It's okay.
Okay.
Thank you.
Okay. Introduction to GSAS-II. I'm going to actually talk a little bit about the background for it, which is the original GSAS. And I talked about that icon. This one was simply handmade. You just draw a little picture with 4 balls, different colors, and a bunch of sticks, and that was the icon. Okay, GSAS was written by Alan Larson and myself. And the history of it is that in the early middle 80s, so it's a long time ago, he and I were contractors at Los Alamos. I was spending summers up there from Arizona State, and he was a year-round contractor. He was responsible for the single crystal instrument. I was there helping to do software for fraction. And the group leader, Richard Silver, came to us and said, we want you 2 guys to support the computational aspects of these 2 instruments. So Alan and I looked at each other and said, why do 2 code? The math is all the same. Structure factor is a structure factor. Right? Bond distances are bond distances, whether you talk about pattern diffraction or single crystal. So we said, let's make 1 program. And the key thing here was that is the data sets had multiple data sets, particularly the single crystal one, where each position of the crystal, there was a data set collected of 100 spots or 1,000 spots for each setting of the crystal. And those spots had different wavelengths because it's neutron time flight, which is really complicated. And you had to treat them separately as individual data sets. So we had to put together a program that will allow you to process multiple data sets. And the neutron time of flight fractometers were the same thing, not quite so many, where you had detector banks at various angles that were fixed. You didn't move them, didn't have to. Because the time of flight gave you that extra variable. But a detector at 90 degrees gave a very different pattern from one at 150 degrees. So to put them together, you had to treat them as 2 separate data sets. So anyway, multiple data sets, neutron pattern, single crystal. We wrote the thing in VAX Fortran because that was a computer at the time. We used something called indexed sequential access method file structure, which means each record in the file had a key and then data and text. And so if you've ever used the old GSAS, you'll see there's something called an experiment file, which contains these records, these so-called ISAM records. And so that's how we organized the data in the control file, because we needed something where you could access a record randomly out of this data set, rather than reading them in sequentially like c.l.s and full prop and a zillion other computer programs do it. We had to be able to jump around and refer to individual records. The calculations were by batch. You set them up, you send it off, and you wait and come back with a result. It was messy because of this. There were multiple data sets, and for pattern diffraction, there were multiple phases. So when you put those 2 things together, you wind up with a horrendously complicated control file. Not like anything else that anybody else has tried to make. So we wrote a menu-driven editor called ExpaEdit, which was about taming that file. So this thing would ask questions of the user, and it would take care of the bookkeeping to make sure that all the entries in the experiment file were correct. And the interface looked like this. Anybody use this thing? Anybody? Yeah, some people way in the back. They'd recognize what this is all about. This was a menu-driven thing, which the menu was accessed by single-letter keystrokes, And you could type ahead from one menu to the next. If you knew what the next menu was, and with a little practice, you would begin to recognize that, oh yes, if I type, L, then I'm going to get the next menu is going to look like this, and I need to type A in order to get it atoms, and then there's a list of atoms. So you learn to type in advance, keystrokes ahead, in order to go in, set some parameters, and get back out. And it was a tree structure, so that you started off here at the main trunk, and you worked your way up various branches. And in order to go from one branch to the next, you had to come back down and then go back up. This was state of the art in the 1980s. This is what commercial computer codes used for their interfaces, was this kind of stuff. Well, in around 1990s, Brian Toby came along and wrote this GUI interface called EXP GUI, which basically did the same thing this did in a somewhat more friendly user interface. So here we are, 1986 to 2004, VAX, Fortran was then converted to IREX, and I had to write a ISAM emulator. So this is Unix or Linux. That allowed a version that was capable of running on a PC, and maybe on a Macintosh. Macintoshes are just strange. I thank Steve Jobs for that. They're just too strange to be believed. This, then what was added was constant wavelength neutron data capability and X-ray diffraction. New profile functions got developed as people out there developing. This is a time when Thomson, Cox, and Hastings and Finger, Cox, and Jeffcoat did their work. And so all of those ideas were embodied into GSAS as they sort of were developed. This is also where I put together the spherical harmonics stuff and actually started doing work with proteins with GSAS. So all of this stuff required code. This thing was easily scripted because all you had to do is script the menu stuff, tell it to execute something, write some more script, interfacing with ExpaEdit, and you could write things with the process sequential data sets. The documentation is not a publication in the literature. It's this manual, which went through about 10 editions or something like that. And this is widely accepted by the community, and it's still being cited 300 or 400 or 500 times a year. It's just amazing. So there's way more than 10,000 citations for this particular stuff. And in fact, we really don't know because an awful lot of people used it and never bothered to cite it. So, but you could tell by looking at the paper that, oh yes, that was GSAS. But there were limits. It was strictly limited to 9 phases and 99 histograms. And that was because of the construction of the keys in that ISAM file. Just wasn't enough room to get anything bigger than that. The interface was dated. Expert GUI is probably going to have to fade away because the underlying codes that support it aren't supported by anybody anymore, and just die. The Fortran stuff probably won't work after a while on many computers. They don't work on a Macintosh anymore because the underlying libraries don't exist anymore. That's what it is. There was nothing for indexing or solving structures, nothing for 2D detectors. So we needed a new program. And after an awful lot of fluffing around, Brian and I put together GSAS-II. It's open source. You get the source. You get the Fortran source, you get the Python source. So you can actually look at our code and say, oh, that's how they did that. Through it. It does all kinds of diffraction analysis, basically from reading in the raw data to doing the graphics for publication, including a whole lot of things that are not in the original code, as you'll see in a few minutes. You can process very, very large numbers of data sets into the thousands. There's literally no limit until you run out of either disk space or computer memory. It's written in Python, and I'll tell you why in a few minutes. Anything that's got a table of numbers, you get a picture. The parameters we try to make them make sense, like microns for size, microstrain for microstrain, and so forth. It's designed around a GUI, and we want it to be friendly. And I started working on it in 2008. By 2008, I was probably like 70, 75. Not a new guy, but it's there. So why Python? This, by the way, is a plot that was produced by a couple of crystallographers who looked at languages and said, you know, how easy it is to write code versus how fast does it go. Python is slow because it's an interpreted language. So in other words, you don't write loops in Python if you can avoid it, because it's going to sit there and work its way through all those lines. There's no compiling or anything like that. So it's slow, but it's really easy to write it because it's a well-crafted language, easy to understand, easy to lay out. These two favorites from the computer scientist crowd are to have various performances depending on how well or badly they're written. Fortran is fast, hard to write, as you can see here from this scale, but is the fastest language there is. It's faster than either one of those two properly crafted. And the reason is because this is old and very, very highly optimized. And it's a very simple sort of compact kind of language. If you want something faster, you have to write it in either assembly or machine code. And for those people who have used Topaz, guess what Topaz is written in? Maybe even some of that. Okay, only works on Windows. Java, another favorite of the computer science crowd, is not only slow, but it's hard to write. So you don't write crystallography stuff in Java. Not if you're in the right mind. However, with Python, if you add this package, which does large array processing, I'll show you an example of that in a few seconds. You can then get code that's just as fast, almost as fast as Fortran. Because in one line, you can take one array and multiply by another. Or in one line, you can do a Fourier transform of a 4-dimensional object with 1,000,000 points in it. It's just that quick. Okay, so here's the example. This is charge flipping. What's the algorithm look like for charge flipping? Basically, what you're doing is you're computing a map, take all the negatives, make them positives, do the reverse Fourier transform to get structure factors back, recover the phases, apply them to the original structure factors, generate a new map, and just repeat. You just keep doing that over and over and over again. What happens is that the sort of messy sort of stuff that winds up resolving itself into peaks and with a relatively flat background, and you have a crystal structure. Seems like magic, but I'll actually talk a little bit about it on Thursday. But here's the algorithm. You begin with a set of structure factors, expand it out over the full sphere, and expand it out into a box, which is out to 1/2 of the 1 over the resolution, typically half an angstrom. So it's millions of points. And the reason why you have to do that is because when you do a Fourier transform, you get an electron density map, which has points in that sort of density of points about every quarter of an angstrom. You just need the same points. So anyway, that's what you start with. And you do this fast Fourier transform, which converts structure factors to density. Get the standard deviation of the density because you're going to use that to establish what the flipping is. That's what this is. This is basically a big if statement that says all those points inside that which are greater than something or other, leave it alone, otherwise flip. Okay, there's another one where it works basically the other way around, which if it's too big, flip that back down. And what that avoids is a solution which has all the density, all the scattering density into one big peak, and you know the structure someplace, so-called uranium solution. So anyway, that's what that's for. So you now have a set of a set of densities which have the negatives removed. You do the inverse Fourier transform right there. One line. That gives you a set of structure factors. You then pull out the phases for it, apply the phases to the old structure factors up here, and a little bit of housekeeping stuff, and repeat. So it's about what? Less than some lines. And it's about a second a cycle for on an old laptop. It's probably faster than the one I've got back there for 500,000 lessons. It does require a lot of memory. It's all double precision. Okay, here's another one. There's something in biological crystallography called an omit map. And it's a little bit like a Fourier map. And basically what you do is, here's the algorithm. Basically, you calculate the map. You chop the map up into boxes, which are roughly 5 angstroms on the side. Now, remember, unit cells are 100 or so. So that's a whole lot of little boxes. And for each box, you flatten it out, leave all the rest of them alone. Do the inverse transform to get the phases. Apply the phases to the structure factor. That calculates the contents of that box. Keep the box, toss the rest. Okay? Then you go to the next one and repeat. And you do this box by box through the entire thing. Put all the boxes together, and that's your new map. And it's the least biased electron density map that you can produce. Because what's in there doesn't depend on what's in there, it depends on what's around it. Now, there is a library of software used in macromolecular crystallography that's associated with something called CCCP4, which is computing, crystallographic computing program for something. I forget exactly what it stands for. It covers 114 pages of printout and about 80 lines a page. That's 9,000 lines of code, which is Fortran and some C. Okay? And you can't use it for non-protein structures because it's really hard to get into it. In GSAS Python, I did the whole thing in 65 lines with another 80 lines to export it into a format that can be used. That's universal for all crystal structures. 65 lines as opposed to 9,000. And my question is, which one is easy to understand? And probably the Python one is just as fast as the big fancy Fortran. Anyway, the design, there's 3 frames that you see, 3 windows, if you like. One is a plot. The other is a console, which contains error messages. You cannot put anything into the console. You can't type something in, do something. Just tells you stuff. And this is composed of 2 pieces, one of which is a tree of the information that's in your project file, which has got things like controls and constraints, powdered, diffraction data, phases, and so forth. When you pick any one of these things, this window will display the contents of that item, whatever it happens to be. And the menu, the menu will reflect the kind of things you can do to it. Now, there's two pieces to the menu. This piece doesn't change because there's sort of global stuff like compute, do a read, refinement, or what have you, import data, export data, so forth. This piece is a submenu that's associated with whatever's here. So you can do things in here like copy information from one thing to another, save it, whatever, set flags for refinement, that sort of stuff. So this changes with whatever is selected here. This thing then contains the information that's associated, for instance, with this phase under the so-called general information. The stuff which is in white boxes, you can change. The stuff which is in gray boxes, which is most of it, you can't change. Except maybe these guys. Okay, this is the general. Right, that's how it's laid out. Graphics, the plot window, powder patterns, waterfall plots, contour plots, crystal structures, the usual ball and sticks and ellipsoids, but also you can draw polyhedra if that's useful. And you can also draw electron density maps if you happen to have a Fourier map calculated. And this is then a slice of the Fourier map, which is in the plane of this of that structure, centered on that point, which is the viewpoint thing that you're actually looking straight at. You can move that around. You can rotate the structure. And the contour stuff all follows with it. Okay, more numbers. Here's microstrain surface coefficients. There's the surface. Here's the texture coefficients of spherical harmonics. You can make sense out of those. You're a better man than I. And here's an actual whole figure that we represent. Much easier to deal with. I talked about that already. Okay. A few years ago, Brian and I got awarded the True Blood Award by the American Crystallographic Association for developing GSAS-II, and they wanted us to have an article in the ACA Reflections, particularly a cover picture. And so we asked our users to send us images of things that they thought were significant in GSAS-II. Most everybody sent multiple images of multiple data sets, hundreds of powder patterns in some cases. I threw in this little guy here, which is, you'll see that a little later on, and also this little guy. Joel talked about a structure with a crazy lattice parameter of 50 angstroms or something like that. This thing is a mineral found in New Jersey, which is it's all in there. Basically, it's a laundry list of elements. Principal things are arsenic, manganese, magnesium, a little bit of iron, oxygen, of course, that sort of stuff. The unit cell for it is 8 by 8 by 203. Ridiculous. Turns out someone has already done the crystal structure, a single crystal structure of it in the rhombohedral space group R3 bar C, centrosymmetric. And it has got disorder in it. And when I looked at it from high resolution powder diffraction data from 11 BN, absolutely spectacular pattern because it's very sharp. And the lowest peak, which is the 006, no less, is down behind the beam stop. Okay, so I only see a bit of it, part of it. And so we indexed it, solved it by charge flipping, and it came out in R3C, non-central symmetric. And most of the disorder in the single crystal structure went away. So that's the same lesson that we heard about this high TC superconductors. The single crystal result was confused by twinning. Here, the single crystal result was also confused by twinning. And it's a so-called marahedral twinning in which the two twin members exactly overlapped in the diffraction pattern. So it looks centrosymmetric, but it's not. Anyway, that's the story there. Refinement in GSAS-II, you saw this. I'll tell you what, since lunch is here, I'm going to skip the stuff about least squares. You can study that on your own. But the point is, it's non-linear least squares, which means you have to cycle around, because what you're actually determining in the least squares is the shift in the parameters, not the values of the parameters. If it was regular linear least squares, like one of those curve fitting straight lines, for example, you don't do it this way. It's by the more simpler approximation. Anyway, what you're after is the shifts and not the values. And when the shifts become not just the math that's done, the key point about all this stuff is how those matrices are built. And basically, in order to solve the thing, you have to invert the A matrix to give you the inverse one. That, by the way, is what the covariance matrix is. And that gives you a set of delta P's down the diagonal, and you simply repeat it until delta P is too small to bother with. In GSAS, the old GSAS, the algorithm processed the powder pattern point by point, went across the pattern, calculating structure factors as it went along, and did it point by point. And in Fortran, that was fast. In Python, no. So in GSAS-II, we do this reflection by reflection. So if you calculate across the whole reflection profile, you dump the whole thing into the least squares matrix, this guy here. Because we can calculate for each peak, you can calculate the partial derivative of that, of each point in that pattern with respect to each parameter multiplied by the other one. And there you get the covariance, the least squares matrix, so-called Hessian. So you just process your way across. Good. Yes, that's the last one. So GSAS does this and creates a thing called a Jacobian, which is parameters along this axis, observation axis this way, and the things that are in here is the partial derivative of whatever the intensity is here with respect to each of the parameters. Big matrix. So you can imagine for 11 BM, a typical powder pattern's got 40,000 points in it. So this axis is 40,000 points. This axis then is the number of parameters in the refinement, which could be 100 or so, or a couple hundred. So this is a big matrix. If you take this guy and multiply by its transpose, that, you get this. And then if you do have another histogram, you just repeat the process. You slap the new one on top of that, and you build up the squares matrix that way. Okay. The inversion, the solution of this is given here. And it's a so-called Liebenberg-Marquardt algorithm with a little wrinkle for singular value decomposition built into the middle of it. The algorithm is basically this. Is you compute the matrix, you normalize it, and the reason why you do this normalization is because the range of values inside this matrix could cover 16 or 20 orders of magnitude for pattern diffraction. It doesn't do that for single crystal diffraction, but definitely does it for pattern diffraction. Computers don't like that big kind of range. So basically what you do is you normalize by square root of the diagonals product. And that makes the diagonal 1 and all the terms scale down from that. Makes it easier to convert. You pick a damping factor and you make a modification to the diagonal. You add a little bit to it. You make an inversion, solve for delta P, apply it. If it increases, you go back and make lambda bigger and do it again. If it goes down, you then apply the shift and you go back up here and make a new matrix. So it's a lot more complicated than the simple least squares because it's going to jump back and forth between making this and doing these kinds of calculations here. This stuff in here is all pretty fast. That's not. So the amount of time that it takes to do this sort of depends a great deal on how well it does the minimization. This whole thing is in about 40 or 50 lines of Python, making use of the NumPy package to do matrix multiplications. And it's all double precision. And this thing is really robust. This is sort of industrial strength damping. And so you don't have to have damping factors. I'm not going to bother with that. You can read about this. In GSAS-II, there's 4 possible choices for the algorithm. The analytic Hessian, which is what I just described. Analytic Jacobian, which is one that's built into Python itself. So we just use that one. Hessian SVD, which is sort of skips the Liebenberg-Marquardt part, just the straight leaf squares. This one's suitable for single crystal work, I think. And then there's numeric, which I don't recommend because it's used for us for testing purposes. It's dreadfully slow because it does a numerical evaluation of the derivatives, parameter by parameter. And we just use it to test. Okay. A little bit about the error estimates. Thanks to Walter Hamilton back in the 1950s. And given a whole lot of observations relative to parameters with distributions that have finite second moments, then the parameter estimates come out of the diagonal terms of the matrix here when normalized by the reduced chi-squared, which is this guy here. And by the way, there is no justification for rescaling these for any such purpose. The key point is this one right here that's in red. Is if there are systematic errors because the model is incomplete, then the values could easily be way beyond their estimated standard deviations from the truth. So it's that's the problem. So the rest of this is simply a long table of the kind of things that GSAS-II would do, and I'm not going to read it. You can look at it and say, oh, that's cool, or why, or whatever else you want to say to it. Except for here, if you have multiple data sets and there's no maximum number, you can do, if you have a lot of images, you can do strain fitting and pull out 3 strain tensor elements for each image. So if you've got something which you have stretched and pulled on it or done something like that in situ and taken series of snapshots as you did this to it, then you can pull out what happens to the strain tensor. If you have one-dimensional patterns, more typical, you can do this for individual peak bits. You can do readbelt refinements over multiple data sets. You can process small angle data sets and do model fitting over a sequence of data sets. And the same thing with reflectometry. The results from all these things are plotted or put into a table, and you can plot any of the columns of the table. So a column might be some parameter that varies with respect to, say, temperature. So you can plot that variable versus temperature and see how it varies. You can then fit it with some sort of a function that you think describes the underlying physics, whatever it is that happens. Now, this is distinctly different from so-called parameterized fitting, in which the model includes that mathematical function, try to describe the variation with a pre-constructed model. The two methods, if you have the model correct, the two methods will give you exactly the same result. But this is a lot more robust, and it also avoids surprises. What else have we got here? A little bit of word about tutorials, only that there is like more than 50 tutorials that describe various bits and pieces in GSAS-II. Joel has a set of tutorials that I think he's going to ask you to look through. But if you go away and say, oh, I want to try the ones in GSAS-II, these are the ones that you should sort of start with, which is basically doing readbelt refinements on various kinds of data. There's a whole bunch of them. All sorts of that. Thank you and have lunch.
Just
Questions?
the next.
You never shout because I'm deaf.
Just a very quick question. For the strand fitting, is it possible to distinguish between the deviatory strand and the dilatation? So when related to the shape change of the unit cell, the other
Perfect. The closest one is that way, where you find those.
Yes.